So these are good examples of wave interference. This is a still photo, obviously, of a disturbance and another disturbance, creating concentric waves, and their crests and troughs are overlapping. Here's an animation showing the same. I'll get back to this in a minute, but let's talk about what kind of interference is taking place in these examples. There are two types. One of them is productive and one of them not so much. So constructive interference results when you have waves adding. This results when a crest of one wave meets the crest of another. So here we have crests lining up, troughs lining up. So you get a reinforcement and you get a bigger wave as a result of that. Obviously, the opposite of that is destructive interference, where a crest meets a trough. And what can happen there is you can get a cancellation. So in the images that I was showing you before, you might see kind of the dark areas here, which might represent the crest adding, and then the lighter areas where the troughs. It's kind of hard to tell exactly. But in this video, you can somewhat see regions maybe radiating outward like this, where there's destructive interference. And then in between those regions, you see constructive interference. So if you look carefully, you can see regions where that happens. It's interesting to note that if you have speakers in a room and they're creating sound, that there are certain areas within the room that are louder than others, at least for certain frequencies. So you can let this represent one speaker and let this represent another speaker, and a person standing here might hear a different loudness than somebody standing over here, for example, depending on whether in the lighter or darker area, or whether, what the pitch is of the tone. Regardless, sound and water waves interfere in the same kind of way. Light does the same thing. In this next slide here, I'm discussing some of the concepts in chapter 19 involving standing waves. When you send a wave down a media and it bounces back, so we have an incident wave and a reflective wave, and they interfere with one another, both constructively and destructively, what can result is what's called a standing wave. So you have an incident wave going this way, a reflective wave going that way, and you can get these loop patterns going on. I'll show you some other modes of vibrations of this loop. It's reminiscent or reminds us of guitar strings, and that's exactly what happens. You have different modes of vibrations in guitar strings, just like you would have in this rope as well. So a standing wave, the definition, it's results from waves traveling in opposite directions and constructively and destructively interfering with one another. We have examples with guitar strings and organ pipes, so they happen with both transverse and longitudinal waves. And also, don't forget that the definition of nodes is where you have zero amplitude. So this really, I guess, has three nodes, one here, there, and there. An antinode is a region where you have maximum displacement. So there's one antinode here and one antinode there. This is a good animation from Excel showing two waves traveling in opposite directions. They're both positive in their amplitude, so you can see that the result right there is an increase in amplitude. If one of them had a negative amplitude, then they certainly cancel out in the middle and go flatline instead of rising up to a higher peak level. This is an example of two waves traveling in an opposite direction. The top one going to the right, the bottom one going to the left. The blue one is the additive sum of the two. In your first lab, what you're going to do is be graphically adding up waves and looking for cases where you have constructive and destructive interference. In the case of a standing wave, you have both happening over time. So when you get maximum displacement right there, and there, and there, that's constructive interference. But when that blue line goes flat, that's where you have the destructive interference happening. This is a clear example of constructive. This is a clear example of both resulting in a standing wave. By both, I mean, constructive and destructive. Okay. So more on standing waves. That's a really interesting situation that you could try. I usually try it in class with a rope, where we just make one loop across the room, like a tube or a rope, and you kind of rotate it. It's not really side to side like your author says. I'd more like create a rotation here. If you do it kind of slow, you can make one giant loop. It's just like a big guitar string, low bassy sound. like that. But if you shake the tube at the right frequency, you can set up a second mode of vibration. So this is like the first harmonic and the second harmonic, third harmonic. In each case, you have to oscillate this at just the right frequency. Otherwise, the standing wave will not be set up. If you shake the tube with twice the frequency, going from here to here, if you double the frequency right here, then the wavelength is cut in half. Now let's verify that. This right here is a node and another node. So this is really just half a wavelength. And this right here is one wavelength because we got node, skip a node, and go to another one. So this one right here, this one has half the wavelength than that guy right there. And you have to oscillate it twice as fast. So there's this indirect relationship between frequency and wavelength. Indirect. Remember that. It's not direct, but an indirect. If frequency goes up, wavelength goes down. So what do you think the frequency of this one is? Higher or lower? Turns out, I just kind of did a Dora Explorer thing, didn't I? I was kind of waiting for you guys to answer. Okay. If you shake the tube with 3 times the frequency, then it's 1/3 of the wavelength. So you can see it's a shorter wavelength than what we had up here. This wavelength would have went, if we wanted to have one wavelength, it's got to go all the way back over here. That's one wavelength. So this is only half a wavelength. This one has like 1.5 in that area. All right, we'll be talking about the Doppler effect next.